Alright, we finished this chapter going over equations that involve rational expressions and then some literal equations. Let's start here with an example that has the variable in the base raised to a rational exponent. Remember what 3/4 means as an exponent. It means the expression is cubed and you're taking the fourth root. That's the index of the root. So what I'm going to do is first isolate this expression that has this rational equation by getting rid of the 2. That's times it by dividing. And I have the quantity x minus 4 to the 3/4 is equal to 27. At this point, I have to get rid of the, because I want to get the x all by itself, I'll have to get rid of the minus 4, but I want to get rid of this exponent first. To undo an exponent of 3/4, I use the property, the power of a power property of exponents by thinking, what power could I raise this so that if I multiply the exponents, power to a power, I would get an exponent of 1. Well, I would need the reciprocal. The reciprocal, of course, of 3/4 is 4/3. So I'm going to raise both sides to the 4/3 power. Now x minus 4 raised to the 3/4 raised to the 4/3 power to a power. This is x minus 4 to the first power. Over here, this is the cube root, that's the index, of 27 raised to the 4th power. And this becomes just x minus 1, of course. And over here, the cube root of 27 is 3, and 3 to the 4th power is 81. Now I can finish this off by adding 4 to both sides. Oop. Adding 4 to both sides. And I have x is equal to 85. I feel pretty comfortable with that answer, but the best way to make sure is to plug it back in and check. If I plug 85 into here, 85 minus 4 is 81. 81 to the 3/4, that's the 4th root of 81, 3 cubed, 27. 2 times 27 is 54. I kind of did that one in my head, but you can work it out on paper, and your solution set is to set 85. Over here now, we're looking at literal equation. Yeah, by the way, before I get past this, my power that I raised both sides to had a denominator of an odd number. So that meant that the index of the root was an odd number. And when you have an index that you have like a cube root or a fifth root, an odd root, then it doesn't matter if the expressions are positive or negative because you can take the odd root of it. But if you have a denominator that's an even number, you better be very careful about what you're taking that root of. You may have to end up picking up like a plus or minus. Back over here now, the literal equations are typically just kind of a catch-all phrase for formulas and such. We get the word literal from the same Greek word that we get the word letter. And so there's lots of letters, lots of variables. So we're going to solve for an indicated variable. In this first example, we're solving for v. In the second example over here, we're solving for p. And it will always give you which variable, otherwise we'd have different answers. There is a stipulation here that in this problem, v is greater than 0. And you'll see where that comes into play in just a minute. But I'm going to isolate the v. I think I want to get rid of the 1/2 by multiplying both sides by 2. Let's make that a little bit bigger there. And 2e would be equal to mv squared. Now I'm going to divide both sides by m. And I think I'll flip the sides around. All right, v squared is equal to 2e all over m. Now here's where I would take the square root of both sides. Now we've done this when we were doing the square root property to solve quadratic equations, and we picked up a plus or minus. But we don't pick up the plus or minus here because it's indicated that v is a positive number. So just the square root of 2e all over m. Now that's not the world's worst looking answer, although I didn't write it very clearly. But there is a fraction under the radical sign. So what I can do here is I can rewrite this as the square root of 2e all over the square root of m, and rationalize my denominator by multiplying top and bottom by the square root of m. So I have the square root of 2em all over m. And that looks maybe a little bit nicer. Now the next one's got a bit of a twist to it because the variable that we're solving for is written twice. And it's not like I could factor out just a factor of p and have it written one time. This is p squared, this is p. So what I'm going to do here is I'm going to subtract k from both sides. Normally we try to get everything away from the variable, but in this case I'm bringing it all over. And I have the weirdest quadratic equation you've probably had to deal with in some times. This is my variable squared, this is my variable, this is my constant. So A is C, B is opposite of D, and C is opposite of K. Remember? Ax squared plus bx plus c equals 0. We could use the quadratic formula. Well, this is my A, this is my B, and this is my C. I'm going to plug right into that formula, but not x equals, my variable is P. P is equal to the opposite of B. The opposite of D is D, plus or minus the square root of B squared, so that'd be the opposite of D squared, minus 4 times A, which is C, times C, which is the opposite of K. What a mess. All over 2 times A, which is C. It sounds almost like I'm messing up here, but these are the coefficients, A, B, and C here, from the standard form. So now I'm going to simplify this if I can. The opposite of D squared, negative times negative is positive, I can just write that as D squared, minus 4 times C times the opposite of K, negative negative, I'm going to write plus 4 CK, all over 2C. Now I don't see anything simplifying in here. You can't take the square root of just this term. It has to be a factor, so I think that's as far as that one's going to go. And that's the last example for this particular section, a very long section on solving equations where our solutions are real numbers.